Hey guys, and welcome to one of the most practical training courses produced by MR-CFD company. In this course, we want to introduce the dynamic mesh model. This module is one of the most important and widely used modules of ANSYS Fluent software, but nevertheless, working with this module is difficult and requires lots of practice. So in this training course, we will provide you with comprehensive and complete training on the concepts of dynamic mesh model. So let's just review the outline of this training course. In the first chapter, which is dedicated to dynamic mesh concepts, we just overview the dynamic mesh model and have an introduction to mesh update methods including smoothing, layering, and remeshing, and also an introduction to optional dynamic mesh models, which includes in-cylinder, 6DOF, implicit update, and contact detection. And at last, introduction to dynamic mesh zone settings, including stationary zones, rigid body, deforming, and etc. Within the next chapters, we got some practical examples for different models. In the second chapter, example 1, we will simulate a cylinder piston motion, which is related to in-cylinder model. Next, in the third chapter, we will simulate a self-propelled submarine motion for the 6DOF model, and in the chapter 4 we will have a simulation of opening and closing of the check valve, and in the next chapter, which means chapter 5, we will simulate the external gear pump using ANSYS Fluent software. And at last, in the last chapter, I mean chapter 6, we will simulate a wave wall. During this example, a wall has a wave motion over time. The first question that arises is when we should use the dynamic mesh model. Suppose you're going to simulate a model in ANSYS Fluent software where the meshing of the model must undergo momentary deformations. That is, over time, the meshing structure in the computational domain of the model is displaced or deformed. This happens when you have a boundary in the computational domain of the model that shifts over time. For example, a certain boundary has rotational or translational motion. This rotational or translational movement causes the meshing in the area around its moving boundary to undergo deformations at the same time. In such cases, we should employ the dynamic mesh method to provide the software with the ability to change the mesh grid of the computational area over time. By now, you've got a big picture of what dynamic mesh module is or where to use it. In the following, we intend to provide comprehensive information about the dynamic mesh module in ANSYS Fluent software. So first of all, we must activate the dynamic mesh module so that the settings related to the definition of the dynamic mesh are activated in the workspace. Notice that you can find dynamic mesh on the left side of the Fluent workspace. In the upper left box of the dynamic mesh model settings, we specify the mesh update methods. It means to specify how the meshing of the model and its cells are updated when the computational area or its borders are displaced or deformed due to the use of dynamic mesh. There are 3 methods available for updating mesh, which include smoothing, layering, and remeshing. Each of these 3 methods uses its own principles and techniques to update mesh cells, and each of them has its related settings. In the following, we want to review these 3 methods one by one and talk about their performance in full detail. The first method is called smoothing. In the smoothing method, the internal nodes of the mesh are only moved, but the number of the nodes and their connections do not change in any way. In fact, in this method, the internal nodes absorb the so-called boundary displacement and its effect on the mesh cells. But a smoothing method itself consists of 3 different methods, including a spring Laplace boundary layer, and diffusion, and linearly elastic solid. First, let's choose the diffusion and smoothing method to provide explanations about it. In this method, the governing equation related to the movement of the mesh is presented as follows. In fact, this Laplace equation specifies how the boundary motion is diffused into the deforming mesh. In this equation, U is equal to the mesh displacement speed. Additionally, the diffusion coefficient or gamma controls how the boundary motion affects the internal mesh motion. This coefficient can be a constant coefficient. That means that the boundary motion is spread uniformly throughout the mesh, or it can be a non-uniform coefficient, which represents that the mesh nodes in areas with high diffusion tend to move together. Just in parentheses, there is a minimal relative movement between them. In the diffusion function section, there are two different formulations for the diffusion coefficient, or gamma. In the formula, as can be seen, the diffusion coefficient is a function of boundary distance, where d is equivalent to the normal boundary distance. In fact, we can control how the boundary motion spreads or penetrates into the domain as a function of the boundary distance. So, in some areas of the computing domain that are located at a distance from the moving boundary, the spread decreases, the same as the formula shows. Of course, this reduction in spread far from the moving boundary makes these areas, areas far from the moving boundary, absorb the movement of the mesh more. This means that these areas will change the quality of the mesh more than other places because less diffusion reaches them, while the areas closer to the moving boundary are better able to maintain their mesh quality because the diffusion is fully applied to them. Also, in this formula, alpha is equivalent to the diffusion parameter, which is determined by the user as an input parameter. In fact, we can manipulate the diffusion coefficient, or gamma, by just adjusting the value of this alpha. Note that it has a value between 0 and 2. Its default value is 0, which results in gamma equal to 1, for example. It results in a uniform diffusion of boundary motion throughout the mesh, while the higher value of the diffusion parameter causes the areas near the boundary, moving boundary, to maintain their meshing structure more, and the areas far from the moving boundary, the meshing structure changes the most. In these images, you can see the effect of the diffusion parameter value on the movement of the internal mesh nodes caused by a boundary movement. As it is clear from the images, when the diffusion parameter equal to 0 is used, uniform penetration of the boundary motion into the inner mesh occurs, so the meshing structure of the model will be uniform. To evaluate the boundary distance d in the diffusion-based method, there are two methods available in ANSYS Fluent software. By default, the software uses the standard mode, which corresponds to the normal or perpendicular distance to the nearest wall boundary, without considering other boundaries such as inlets and outlets, symmetry, or etc. But there is another method that is disabled by default, and if needed, the generalized boundary distance option should be activated. In this method, d is the normal distance to the nearest boundary, but regardless of the boundary type. In the second formula, the diffusion coefficient is a function of the cell volume, where V is the cell volume. According to this formula, we can control how the boundary motion propagates or penetrates into the domain as a function of cell size. Therefore, in some areas of computing domain where there are larger cells, the spread decreases, the same as the formula shows. Of course, this reduction in diffusion in larger cells makes these areas, areas with larger cells, absorb the movement of the mesh more. This means that these areas will change the quality of mesh more than other places because less diffusion reaches them, while the areas with smaller, better, and more cells can maintain their mesh quality because the diffusion is fully applied to them. In the end, let's talk about the capabilities and advantages of the diffusion smoothing method. This method is available for all types of cell elements and can update any cell area whose borders are moving and changing shape. This method is computationally more expensive than the spring smoothing method, which will be talked about in a moment, but it likely results in better mesh quality and generally allows for larger boundary deformations before breaking. Similar to the spring smoothing method, this method can control the translational boundary deformations much better than the rotational movement. The diffusion smoothing method is incompatible with the boundary layer smoothing method or the phase region remeshing method. That is, it is recommended not to use these mesh update methods at the same time when using the diffusion smoothing method. In this formula, alpha as the diffusion parameter is determined by the user as an input parameter, and we can manipulate the diffusion coefficient gamma by adjusting the value of this diffusion parameter. If the value of this parameter is 0, it leads to gamma equal to 1. That is, the uniform diffusion of the boundary movement is transferred to the entire mesh. While the higher value of the diffusion parameter causes the areas with larger cells to maintain the meshing structure more, and the areas of smaller cells, the meshing structure changes the most. In the following, we will introduce the next smoothing method, which is known as spring, Laplace, and boundary layer. In a spring smoothing method, the edges between both mesh nodes are considered as a network of connected springs. The initial spacing of the edges before any boundary movement indicates the equilibrium state of the mesh. A displacement at a given boundary node will produce a force proportional to the displacement along the springs attached to the node. According to the Hooke's law, the force acting on the mesh node can be expressed as follows. In the Hooke's law relation, delta xi and delta xj respectively represent the displacements of the ith node and its adjacent node. Ni is equivalent to the number of adjacent nodes connected to the ith node, and Kij is equivalent to the spring constant or stiffness between the ith node with its adjacent node. The spring constant equation for the edge connecting nodes I and j is given. K-fac is applied in the spring constant factor section in the software settings. This factor has a value between 0 and 1. A value of 0 indicates that there is no damping on the springs, and boundary node displacements have a greater effect on the motion of internal nodes, while a value of 1 applies the default damping level to the internal node displacements. In equilibrium, the net force on a node due to all the springs connected to the node is equal to 0. This condition leads to an iterative equation where m is the iteration number. Since the displacements at the boundaries are known, the previous equation is solved using a Jacobian sweep on all interior nodes. So at the time of the convergence, the location is updated in this way, where n and n plus 1 represent the location in the current time step and the next time step respectively. In general, the software solves the previous equation iteratively during each time step until one of the two cases is established, or the number of iterations that we set is over, which is determined by the maximum number of iteration option, or the solution converges in that time step where the convergence limit is determined by the convergence tolerance option. By default, the spring-based smoothing method is enabled for all cell regions. It means that the all mode is active in the elements section. So if you want to disable the spring smoothing method for cell areas that are not completely composed of tetrahedral or triangular cells, you can use the option tet in tet zones in 3-dimensional simulation or tri in tri zones in 2-dimensional simulation. Also, if you want to use mixed element zones and you don't want to use the spring smoothing method on all types of elements, you can use the spring smoothing method only on the cells by selecting the option tet in mixed zones in 3D mode and tri in mixed zones in 2D mode. Finally, here is a summary of the capabilities and advantages of the spring smoothing method. This method is used to update any cell area whose borders are moving and changing shape, but for non-tetrahedral or non-triangular cell regions, this method can only be used if either the border of the cell region moves mostly in one direction or the movement is mostly perpendicular, because if these two conditions are not met, the resulting cells may have a high skewness value. However, the spring-based method for polyhedral meshes causes high skewness under any condition and without these two conditions. Also, for hexahedral meshes, the diffusion-based method is generally recommended. There is another type of mesh update by a smoothing method which is based on linear elastic solids. The movement of the mesh in the linear elastic solid smoothing method is expressed as follows, where sigma is equivalent to a stress tensor, epsilon is a strain tensor, and vector y is equivalent to mesh displacement. Of course, for this equation, the ratio of shear modulus and length first parameter are mentioned, which are used in the form of Poisson's ratio. The allowed range for Poisson ratio is between -1 and 0.5. When using a smoothing methods based on diffusion or linear elastic solid, it is possible to determine a reference position. This feature is useful for cases where there are a large number of periodic movement cycles for static and moving meshes, like turbo machine rotors with blade flutter. In fact, when you ensure that the smoothing method is always performed from a reference location, the quality of the mesh may be more stable from cycle to cycle. Now let's talk about the capabilities and advantages of the linear elastic solid smoothing method. Most of the features and limitations discussed in the diffusion method are also applied to the linear elastic solid method, especially the reduction of the mesh quality in the rotational movements. The linear elastic solid smoothing method is more expensive than the diffusion method in terms of computational cost, but for some meshes and mesh movements, it maintains the mesh quality better. This smoothing method, having constant material properties, can be considered a limitation compared to the diffusion method, which has non-uniform diffusivity. In addition, the linear elastic solid smoothing method can use triangular or quadrilateral elements in two-dimensional models, and tetrahedral, hexahedral, wedge, and pyramid cells support in 3D models. But this method cannot be applied to cell regions undergoing deformations, including hexagonal cells or polyhedral or hanging nodes. In these cases, the diffusion smoothing method is applied. In addition, the linear elastic solid smoothing method is incompatible with the boundary layer smoothing method or the phase region remeshing method. That is, it is recommended not to use these mesh update methods at the same time when using the linear elastic solid smoothing method. When you use the spring smoothing method, two other smoothing methods are applied to the model simultaneously. One of these methods is the Laplacian smoothing method. Laplacian smoothing method is the most common and simplest smoothing method. This method adjusts the location of each mesh vertex with the geometric center of its adjacent vertices. Actually, according to this method, a node goes to its new location so that this new location is the average location of its neighboring nodes. This method is computationally cheaper but does not guarantee improved mesh quality and can lead to elements with poor mesh quality. In the Laplacian smoothing method, this relation is used to calculate the location of the node, where the vector xi represents the average location of the ith node in the mth iteration, and the vector xj represents the location of the adjacent node of the xi vector in the nth iteration, and ni is the number of neighboring nodes of the ith node. Hence, the new location of the node is calculated as follows, where beta is equivalent to the Laplace relaxation factor. However, note that since the mesh vertex is moved to a new location in this method, the skewness of all planes adjacent to the new location should be improved compared to the previous location. Another smoothing method is boundary layer. The boundary layer smoothing method is used to change the shape of the boundary layer mesh during the simulation of the moving or deformed mesh. For cases where the mesh movement, for example as a rigid body with a certain movement, is applied to a phase zone with adjacent boundary layer, the boundary layers can be deformed by activating Deform Adjacent Boundary Layer with Zone in the Dynamic Mesh Settings section. Now, when the boundary layer smoothing method is activated, the nodal coordinates of each cell in the boundary layer area are updated due to displacement with the same displacement vector. As a result of the boundary layer smoothing method, the cells adjacent to the deformable wall are deformed to maintain the quality of the boundary layer region. Typically, this method preserves the height of boundary layer cells adjacent to the deformed plane region. This view is primarily considered for transitional movement because if the plates undergo significant rotation, the cells of the boundary layer may become skewed. Note that this method is only compatible with the spring smoothing method and cannot be used for the diffusion or linear elastic solid smoothing method. In addition to this method can be applied to the boundary layer areas of all kinds of meshes. By now, you're fully familiar with the smoothing mesh update method and its types. In the following, we're going to introduce the dynamic layering method. In prismatic mesh areas like hexahedral or wedge, the dynamic layering method is used to add or remove layers of cells adjacent to a moving boundary. This happens based on the height of the layer adjacent to the moving surface. So, an ideal layer height should be determined by the software on each moving boundary. For better understanding, take a look at this figure. As it shows, the layer of cells adjacent to the moving boundary, which is layer J, is divided or meshed with the layer of cells after it, which is layer I, based on the height h of the cells in the layer J. Now, if the cells in the J layer expand, the height of the cells is allowed to grow until this condition is met. In the given equation, h mean is equivalent to the minimum cell height of cell layer J, and h ideal is equivalent to the ideal cell height, which can be a constant value or a function of time or even angle, and alpha s is equivalent to the cell division factor. The ideal cell height is determined in the mesh options section of the dynamic zones section. And finally, when this condition is met, cells divide, height-based or ratio-based. If the division is based on height, the cells are divided to create a layer of cells with a fixed height h ideal. But if the division is based on the ratio, the cells are divided so that locally the ratio of the height of the new cells to the height of the old cells is exactly equal to alpha s everywhere. Now, if the cells in the jam layer are compressed, their compression will progress until this condition is met. In this relation, alpha c is equivalent to the layer collapse factor. At this time, the layer of compressed cells merges with the layer of cells above the compressed layer. That is, the cells in the jth layer are merged with the cells in the ith layer. Let's talk about the advantages and capabilities of the dynamic layering method. The layering method can be used to divide or mesh cells adjacent to any moving boundary, of course if these conditions are met. All the cells adjacent to the movable plane area should be wedge or hexahedral, and in two-dimensional models should be quadrilateral. Cell layers must be completely bounded by one-sided planar regions except when sliding interfaces are used. The third and last mesh update method that will be introduced is the remeshing method. When the boundary displacement is larger compared to the size of the local cells, the quality of the cells can deteriorate, or if the mesh smoothing method is used, the quality of meshes can be corrupted. This causes the meshing to become invalid, leads to negative cell volume, and as a result leads to convergence problem when the solution is updated at the next time step. To solve this problem, the software can collect the cells that violate the skewness and size criteria and remesh these collected cells locally. Now, if the new cells can satisfy the skewness criterion, the meshing is updated with the new cells. Otherwise, the new cells are discarded and old cells are kept. When you use the remeshing method for the dynamic region, it is recommended to use the unified method. This method uses an algorithm that combines aspects of a variety of remesh methods and by default tries to preserve the original mesh size distribution even as the mesh moves. This simplifies the modeling setup and increases the resolving power, especially for parallel simulations. Of course, it should be noted that this unified meshing method is only applied to tetrahedral or triangular cells. But if other types of cells you need to be remeshed, you should use the default method-based method. In this case, you can selectively choose the options you want, each of which is suitable for a type of cell. Here are some different methods of remeshing. The local cell method only affects triangular and tetrahedral cells. When using this method, the software marks cells based on cell skewness and minimum and maximum length scales. In fact, the software evaluates each of the cells and marks them for remesh if these three conditions are true. First one, the skewness value of the cell is greater than the minimum skewness set by us. The second one is the cell size is smaller from the minimum length scale determined by us, and the last condition is that the cell size is larger than the maximum length scale determined by us. It should be noted that the cell height cannot reach the maximum length scale. Actually, pay attention to the fact that the marking of the cells is done based on skewness in each time step, but marking based on size and height is done between a specific size remeshing interval, because the change in cell size distribution is generally small during a time step. The local face method is only available for 3D models and can remesh triangular cells and cube cells in boundary layer meshes. In this method, the software marks the cell sheets based on the sheet skewness and remesh them again. This is done based on the maximum skewness value determined by us. There is another feature in the software that instead of making the cells based on the maximum and minimum length scale, the mesh cells can be marked based on the size distribution created by the sizing function. So for this, the sizing function option must be activated. To determine the size function, the software creates a bounding or limited box around the desired region, which is approximately twice the size of the region, and place the shortest feature length within each fluid region. Then the software divides the boundary box based on the shortest characteristic length and resolution determined by us. This will cause the software to create a background mesh. We control the accuracy of the boundary mesh, and it is created for each cell area. The shortest feature length is determined by shrinking the second box around the object and then selecting the shortest edge in the box. This size function is evaluated at the vertex of each background mesh separately. According to the figure you see from the top of the background mesh, the local value of the size function, or SFI, is expressed according to this relation. As can be seen in this figure, the background mesh is the same as the coarse pattern that is created in the background of the main mesh with the small triangular cells, and the central points of intersection of this background mesh is the same as the vertex of the background mesh. In this relation, dj is equivalent to the distance from the vertex I on the background mesh to the center of the boundary cell j, and delta sj is equivalent to the size or length of the mesh of the boundary cell j. After this, the size function is smoothed using Laplacian smoothing method. Then the software interpolates the value of the size function by calculating the distance Li from the center of the given cell P to the vertices of the background mesh that surrounds that cell. This intermediate value of the size function, or size B, in the center of the cell is calculated according to this relation. Now, by using the parameters such as alpha and beta, which respectively express the variation of the size function and the rate of the size function, the final value size p of the size function at point P is expressed as follows, where dB is a measure of the distance of point P from the nearest border, and parameter gamma is also dependent on this dB. In fact, alpha, or the variation parameter of the size function, controls how large or small an interior cell is compared to its nearest border cell. This parameter varies from -1 to infinity. For example, a value of 0.5 indicates that the size of the inner cell can be at most 1.5 times the size of the nearest border cell, and conversely, a value of -0.5 indicates that the size of the inner cell can be half the size of the nearest border cell. On the other hand, beta, or the rate parameter of the size function, controls how fast the cell size changes from the boundary. This parameter is determined in the range of -0.99 to 0.99. So the positive value of this parameter indicates a slower transition from the border to the variation value of the size function specified by us, and totally vice versa. The negative value of this parameter indicates a faster transition. The face region remeshing method is used to remesh triangular faces in 3D meshes or linear faces in 2D meshes that are on a deforming plane region and adjacent to a plane region. They are mobile. The software marks mesh planes based on maximum and minimum length scales and then remeshes those planes and associated cells to create a highly regular meshing on the deforming boundary. In general, the face region method can only be used in cell regions containing triangular cells in 2-dimensional mode or tetrahedral cells in 3D mode. It should be mentioned that this remesh method is not compatible with the diffusion smoothing method or the linear elastic solid smoothing method. The 2.5D remeshing method is only applied to extruded 3D geometries and is similar to the local remeshing method in 2D mode. According to this method, the faces on a deforming boundary are marked based on the face skewness criterion and the maximum and minimum length scales for remeshing. Also, the 2.5D mesh method allows you to mark cells using the sizing function. In fact, this method is the 2-dimensional triangular mesh that is expanded or extruded in the direction of the normal vector of the specific dynamic area that we want in modeling. In other words, the triangular surface mesh is remeshed and smoothed on one side of the mesh, and then the changes are extruded to the opposite side. Alright. After we have provided comprehensive explanations with the details about the different mesh update methods in the dynamic mesh model, we return to the dynamic mesh model settings window. In the upper right box of the dynamic mesh settings, there are options that can specify a specific dynamic mesh models. These capabilities include in-cylinder movement, movement with 6 degrees of freedom or 6 DOF, implicit update, periodic displacement, and contact detection. So first of all, let's begin with the in-cylinder dynamic mesh model. The first thing to say about this dynamic mesh model is that the in-cylindrical model can only be activated for transient problems. When using in-cylinder motion, the software provides a built-in function to define the position of the piston as a function of the crank angle. This function is named piston full and can be selected from the motion UDF4 profile list in the dynamic mesh window as a part of the rigid body motion. When the piston full function is used, the piston position PS is calculated according to this relation. In this relation, RC is the crank radius, which is equivalent to the distance between the center of the crankshaft and the center of the crankshaft pin. L is the connecting rod length, and X offset is the piston pin offset. That is, when the piston pin is vertically offset from the plane defined by the crankshaft axis and the direction of piston movement. This deviation can be positive or negative, and it is determined based on the geometry and direction of rotation of the crankshaft. Also, theta C is the current crank angle. The mentioned current crank angle is obtained by this relation, where theta S is the starting crank angle and phi shaft is the crankshaft speed. Let's just see this figure. When the piston reaches the highest possible point in the cylinder, that place is called top dead center or TDC. That is when the crankshaft pin is completely aligned between the piston pin and the center of the rotation of the crankshaft, and the crankshaft angle is equal to 0. At this time, the position of the piston or PS is equal to 0. This value is also obtained from the equation. Now, when the piston reaches the lowest possible point in the cylinder, that place is called bottom dead center or BDC. That is when the crankshaft is completely aligned between the piston pin and the crankshaft pin, and the crankshaft angle is equal to pi. At this time, the position of the piston or PS is equal to 2RC. As you can see in cylinder window, we need to define parameters such as crank angle, connecting rod length, and piston pin offset based on the formula we provided in the previous slides. There is another parameter which is current crank angle. This current crank angle is obtained according to the formula we presented earlier. In this formula, we defined parameters such as crankshaft speed and starting crank angle. We got another option here which is known as in-cylinder output that can be used when you want to specify certain output parameters. Also, in the setting of this section, the values related to the minimum valve lift and the piston stroke, which is the same path traveled by the piston from 0 to 180 degrees, are controlled with the piston stroke cutoff and minimum valve lift option. By activating this option, the settings window will be appeared. In this section, you can specify the various quantities needed for swirl and thumbbell calculations according to the recording frequency of the output in the selected file. Swirl flow is used to describe the circulation around the axis of the cylinder, while the thumbbell flow is rotating around an axis perpendicular to the cylinder's axis and is orthogonal to the rotating flow. In this slide, we will introduce the quantities that will be stored in our selected file and according to the frequency determined by us. These parameters are crank angle, which is known by Ca, the total mass of the liquid in the selected cell areas, the angular momentum vector of the fluid mass in the selected cell areas relative to the center of the rotation, which is shown by L, the size of the angular momentum of the fluid, axis of rotation or vector Sa, axis of roll, vector Ta, cross-axis of the roll, Cta, moment of inertia of the fluid mass around the axis of rotation, which is shown by Isa, moment of inertia of the fluid mass around the axis of roll, which is shown by Ita, and the moment of the inertia of the fluid mass around the transverse rolling axis, or Icta. In general, for the setting of the dynamic mesh model for an in-cylinder problem, we must consider the following steps. First, how to provide a suitable mesh topology for volumetric mesh update methods, for example, smoothing, layering, or remeshing. Second, how to define motion and geometry characteristics for valve and piston surfaces. And third, how to open and close the intake and exhaust valves. Now let's see a process of dynamic mesh simulation setting for an in-cylinder problem. So consider an example of a two-dimensional in-cylinder model for a typical pent roof engine. So let's start by the mesh topology. We should provide an initial volumetric mesh for the suitable mesh topology for the software, so that different mesh update methods can be used to automatically update the dynamic mesh. However, the software does not require that we set all in-cylinder problems using the same mesh topology. When we create the mesh for the in-cylinder model, we need to consider different areas of the mesh that we can define as moving, deforming, or stationary areas, and these areas of the mesh create with the appropriate cell shape. As you can see in this figure, the image on the right side, the mesh topology shows the different mesh areas within the model, and the image on the left side shows the volumetric mesh associated with those mesh areas. Now we explain what kind of meshing method is used for each area of the in-cylinder model. Because of the rectilinear movement of the moving surfaces, we can use dynamic layering to show the mesh areas that are swept or formed by the moving surfaces. These areas are the same areas on the upper surfaces of the inlet and outlet valves and on the surface of the piston head, and should be meshed with quadrilateral or hexahedral cells. For the inner region of the chamber, we need to define a remeshing region with triangular cells to accommodate the different locations of the valves during the simulation process. In these areas, the motion of the boundaries, valves, and piston surfaces is propagated to the internal nodes through a smoothing. In general, if the cell quality violates any of the remesh criteria set by us, the software will automatically collect these cells and remesh them. In addition, the software deforming faces based on the maximum and the minimum length scale on the cylinder walls and also sections on the sliding interfaces to connect the cell area of the chamber. It remeshes the layering areas on the valve surfaces. For input and output areas, we can use triangular or quadrilateral cells. Because these areas do not move or change shape, the software automatically marks these areas as stationary zones and does not apply any kind of mesh movement method to these cell areas. In the second step, we talk about defining the movement characteristics. In fact, we intend to explain how to define the movement of the cylinder inside the piston and the opening and closing movement of the inlet and outlet valves. When the piston moves down from the top dead center position to the bottom dead center position, we need to expand the meshing area again and develop so that they can accommodate the valves when they are fully extended. To do this, you need to specify the dynamic layering area in the vicinity of the piston surface so that the piston companion moves to a certain distance from the TDC position. Beyond this specified distance, the motion of the layered zone stops and the piston wall is allowed to continue to reach the BCP location. Since there is a relative motion between the piston head surface and the currently stationary dynamic layering region, cell layers are added when the ideal layer height criterion is violated. Note that before using these functions, you must define the parameters used by these functions. For example, you must specify the crank angle, connecting rod length, and piston stroke cutoff in terms of distance from TDC. In the in-cylinder model, the software provides built-in functions to control full piston movement and limited piston movement for the dynamic layering region on the piston surface. We use the built-in function full piston to define the movement of the piston, that is the boundary of the piston. But to define the movement of the inlet and outlet valves, we use profiles that describe the valve lift changes in terms of crank angle. Here is an example of a simple profile. In this profile, the angle should be in degrees and the valve lift should be in meters. In this plot, you can see the diagram of changes on the top of the inlet and outlet valves according to the crank angle. As the graph shows, the peak value is 0 when the valve is fully closed, and the maximum value is when the valve is fully open. In the second step, it is time to define how to open and close the valve. The software assumes that once you set a mesh topology, this mesh topology remains unchanged throughout the simulation. So the software does not allow you to close the valves completely, and that the cells between the valve and valve seat are destroyed when the surfaces are in contact with each other. To prevent this cell collapse, you must define a minimum valve lift, so that the software automatically stops the valve movement when the valve lift is smaller than the minimum valve lift value. By now we are done with the in-cylinder model, and from now on I'm gonna introduce the 6 degrees of freedom or 6 DOF solver and provide complete explanation about the settings of this type of movement. The 6 DOF solver calculates the moment and external forces such as aerodynamic and gravitational forces and moments on objects that are under rigid body motion. These forces are calculated by the numerical integral of pressure and shear stress on the surface of the object. This technique can be easily applied to many useful applications. As you open 6DOF settings panel, you must first create and manage a series of settings related to the properties of the 6 degrees of freedom. In this part, by defining series of data such as mass and moment of inertia, we specify a range of degrees of freedom for a rigid body movement. After activating the 6 degrees of freedom solver, if we create a rigid body in the dynamic mesh zone section, we can use the motion defined by the 6 degrees of freedom solver to move this rigid body. In fact, in this model, we define an unforced motion for the rigid body. In other words, we do not specify the size and direction of the translational or rotational speed for the rigid body. Instead, the 6 degrees of freedom solver determines the motion of the rigid body based on the values defined by us, such as mass and moment of inertia. Therefore, the fluid flow around the desired rigid body creates movement in this body. Also, in this section, you can define the gravitational acceleration based on Cartesian coordinates. Actually, there is another checkbox down here which is called Write Motion History. By using this option, the movement of the object can be saved step by step in the form of a series of history files. Now let's talk about how to create motion based on the 6 degrees of freedom solver to apply it to a rigid body. First of all, the software asks for a name for the desired movement, but for the 6 degrees of freedom movement, mass and inertia tensor components must be defined. Note that the components of the inertia tensor are defined in relation to the center of the gravity and rigid body orientation, which are defined in the settings of the dynamic mesh zone section. Also, if you want the dynamic object to be limited to 1 degree of freedom movement, either translational or rotational, you can use 1 DOF translation or 1 DOF rotation option. In fact, in a real case, an object can have 6 degrees of freedom, which includes 3 translational movements along the coordinates x, y, z, and 3 rotational movements around them. But when we limit the movement of the object to 1 degree of freedom, the object is only allowed to move in one of these 6 directions, and it is restricted and not allowed to move in other 5 directions. Now suppose that we chose the mode of 1 degree of freedom for rotation. For this case, we must determine the mass of the dynamic object and the moment of inertia. For a rotational movement, the axis of rotation should be determined based on the Cartesian coordinates. The sign positive or negative of the value considered for the desired axis indicates the direction of rotation, I mean clockwise or counterclockwise. Of course, in 2-dimensional mode, it is automatically selected along the z-axis. Next, we must specify the location coordinates of the origin of rotation in the center of rotation section. In the 6 DOF solver setting, you have the option of defining a Hooke's law spring that applies forces or torques to a dynamic object. This spring is a compression or extension spring for translational movements and a torsion spring for rotational movements. Furthermore, the mechanism of this spring system is that a specified constant is multiplied by the distance of the dynamic object from its initial location. This resulting force is combined with a preload value that is constantly applied to the dynamic body, until finally the final net loading applied to the spring is obtained. Of course, this preload can be positive or negative depending on the direction. In addition, you can limit the range of motion of the dynamic object by activating the constraint option and defining a reference angle. For example, first, in the value part, we determine an initial angle for the placement of the dynamic object, and by determining the maximum and minimum values in terms of degrees, we set a restriction for the object. So this object can rotate from the initial angle only within the maximum and minimum limits determined by us. Now, after examining the rotational motion of 1 degree of freedom, we want to examine the translational motion with 1 DOF. Almost the setting of translational motion mode are similar to rotary motion, but one of the differences of translational movement is that for this type, only the direction of its movement should be determined based on Cartesian coordinates in the direction section. In addition, in order to limit the transfer movement, we must define an initial location for the moving object in the reference point selection, and then limit the range of movement of this location in a specific range between maximum and minimum, so that the desired object is only within this range to move. Alright, up to now we covered the 6DOF model and also in-cylinder movement, and now we want to talk about the setting of the implicit update mode. When we are modeling transient problems, we can implicitly use the mesh update feature. Actually, the use of this feature is for when we want our dynamic mesh to be updated during a time step, not that is only updated at the first time step. This feature is only useful for applications where the mesh motion is dependent on the fluid flow. For example, cases that use a 6 degrees of freedom solver or cases that include fluids structure interaction or FSI. For such cases and applications, having the ability to update the mesh motion within the time step based on the converged flow solution results in a stronger coupling between the fluid solution and the mesh motion, and results in a more robust solution process for the solver. The implicit mesh update feature allows us to run the simulation process because otherwise it may not be solvable or the time step size may be extremely small. Note, however, that the implicit mesh update mode cannot be used with density-based solver, with explicit view, steady simulations, and in-cylinder application. For the settings of implicit update mode, we must first determine the update intervals, which specifies the frequency and iterations in which the mesh is updated within a time step. For the motion relaxation, which is the relaxation factor related to the movement or displacement of the nodes during the mesh update, we can specify or set a value between 0 and 1. At last, in the residual criteria section, we must determine a residual criterion to be considered as the convergence criteria of the solution process. And finally, the last option we got in the options box is the contact detection. This option is used to detect whether the calculated mesh movement leads to contact of a moving surface with other surrounding surfaces or not. If a contact exists within a certain tolerance, the motion of the moving area mesh can be restricted or constrained using nodal contact information in user-defined functions, or the flow in the contact area can be controlled. In the first step, the surfaces that are involved in the contact detection process from the list of the available phase zones should be selected. Note that you can only select rigid or user-defined downwinds and regions for contact detection. From the UDF option drop-down list, you can specify a user-defined function that will be applied when the contact of surfaces is detected. To activate the contact detection process, you must specify a proximity threshold value. In fact, when the distance between contact regions becomes less than this threshold value, the UDF specified in the UDF drop-down list is loaded. In addition, you can apply flow control in the contact region. The flow control option is applied to the cells that are within the proximity threshold distance of the specified contact surfaces. Now, there are two ways to control the flow, one using contact zones and the other one is using contact marks. So to use one of these methods, activate the flow control option in the contact region section. Let's talk about the contact zones method first. The contact zones method of flow control allows you to modify the flow in the contact surface by creating a separate cell area containing marked cells. The flow in this cell zone may be controlled using the existing cell zone condition. By default, this area is defined as having porous resistance. This method is fully compatible with all modes of the solver. As was mentioned earlier, the other method is called contact marks. The contact marks method imposes a numerical boundary condition of zero mass flux at the boundary of the marked contact region, which blocks the flow. This method has limitations. For example, it is only limited to the pressure-based solver or does not support the quick discretization method. There is also an option called event for dynamic mesh. By using this tool, we can control the time of occurrence a specific event during the simulation process. In the settings of the event section, we must first specify the number of desired events and give a name to each of them. Now, if the flow is inside the cylinder, we are faced with the add crank angle option. That is, we must determine the angular position of the crankshaft where the event occurs. But if the flow is non-cylindrical, we are faced with the add time option. That is, we must specify the time in which the event takes place. Also, the types of the events that we can define for the desired time or angle include things like creating or removing the sliding interface, changing the time step, inserting or removing the cell layer, etc. Finally, it is time to introduce the dynamic mesh zone section. In this part, we have to determine the movement or deformation of the dynamic area inside the model. In fact, in the setting of this section, we specify the type of behavior or the type of movement for different areas of the computational domain. For the initial step, we have to specify the type of movement for the desired dynamic area. There are different types of movement of dynamic areas, including stationary, rigid body, deforming, user-defined, and coupling system. For the settings related to the stationary area, we must first select the desired area that is supposed to be stationary in the dynamic mesh zone section. If the dynamic area is stationary, we have to use a stationary model, so that in static mode, the mesh nodes of this area are excluded when updating the location of the nodes. In other words, mesh update is not applied to them. By default, if no moving, no matter deforming or moving, is assigned to a cell or contact area, that area is not considered in the mesh update time to the next time step. However, there are cases where an explicit declaration of the area of existence is required. I mean, although no movement is applied in the static region, and it may seem that there is no need to define that, but sometimes it is still necessary to define a static region explicitly. For example, if a cell region is assigned some solid body motion, the location of all nodes belonging to the cell region will be updated, even if some nodes are also part of a non-moving boundary region. The explicit definition and declaration of a static region excludes the nodes in these areas when updating the location of the nodes. That is, it makes that area not affected by mesh changes caused by moving or deforming areas. If the corresponding static area is a planar area, you must define a cell height for each adjacent area involved in dynamic layering. Note that this cell height does not affect the cell size for remeshing. In fact, this height is equivalent to the ideal height in relation to the layering mesh update method. Next, if the dynamic area has rigid body movement, we should use rigid body option. It means to consider a region of the model as a rigid body that has a certain dynamic movement. Also, let's just mention that rigid body means a body in which all points and parts are moved or deformed in a unified manner and do not have relative motion related to each other. When we are using rigid body motion, the movement of the dynamic region can be defined in two ways. The first one is using profile or user-defined function, that is, the movement in the form of formula code or defined data ready for the software. The other way is to use 6DOF or in-cylinder tool. When we use 6DOF, the translational or rotational movement of the object is defined by the degree of freedom by the software, based on a series of data that we entered for the software in the 6DOF settings. While when we use in-cylinder model, the software provides a self-generated function that is based on a series of data that we entered for the software in the in-cylinder settings. So let's assume that we want to define the motion of a rigid body using the first method. In order to define, or let's say just compile the UDF into the software, we should use the compiled option beneath the function section. Now, if we want to use the in-cylinder model, we must select the motion defined by the self-made function of the in-cylinder model, which is the same of full piston function. And when we want to use the other method, we can just easily get to the 6DOF settings section in order to find the 6DOF UDF or properties section of the rigid body settings. As you can see in the 6DOF UDF or properties section, we've got a different option which is called the passive mode. This mode is used when you do not want to consider forces or moments on the desired area. Indeed, suppose that we want the region of interest to have rigid body motion, but that rigid body motion is not affected by the setting of the 6 degrees of freedom solver. Now let's just step back and explain the motion of the rigid body when using the 6DOF solver. In the center of gravity location section, we specify the initial location of the center of gravity for the rigid body in terms of coordinates. Also, there is the rigid body orientation section that we specify the orientation of the rigid body in the inertial coordinate system. Furthermore, if you intend to make a rigid body move relative to another rigid body, you should activate the relative motion option. So you had to create a separate rigid body before and consider the motion of the new rigid body relative to it. And in order to do that, you have to select the previous solid object in the relative zone. In addition, when using the 6 degree of freedom solver, we are faced with two options, which include the center of gravity velocity and the rigid body angular velocity. We must determine these velocity values relative to the Cartesian coordinate system. Of course, these velocity fields are omitted when using rotational or translational motion of 1 degree of freedom. But for the adjustments related to the movement of the rigid body when using the in-cylinder solver, we must determine the direction of the reference axis of the piston or valves in the valve-piston axis section. The third type is dedicated to deforming boundary. It means that when we face a dynamic surface which is changing shape, we actually should use this model. For the settings of the changing zone, we must first determine from the Geometry Definition tab the zone of the computational domain of the model that we want to change shape. As shown, there are several modes that we can use in order to determine the desired geometry. If the desired geometry does not exist in the computational area of the model, select the faceted option. If we intend to define our desired geometry as a plane, we select the plane option and create a desired plane by determining the location of a point of a plane and the normal vector of that plane. And if we intend to define our desired geometry as a cylinder, we select the cylinder option and create our desired cylinder by specifying the radius of the cylinder, the origin of the cylinder, and the axis of the cylinder. If the geometry is unspecified and the movement of the mesh normal or perpendicular to the boundary is allowed, we use the unspecified option. Of course, this option is activated only when we use the linear elastic solid smoothing mesh update method. And finally, if we intend to describe the geometry by a function defined by the user, we use the user-defined option. Also, we got another separate option which is called user-defined. For an area or surface or zone that is deforming or moving, you can define the location of each node on that moving or deforming area using a user-defined function. We got another option here which is called coupling system. This capability is used for when the motion is defined as a result of a coupling a specific zone of the computational domain. One of the main applications of the coupling system is to investigate the interaction between the fluid and the structure. In other words, suppose a fluid collides with the surface of a solid body and affects that body, for example, displaces it or changes its shape. On the other hand, any kind of change in the state of the solid body causes a change in the behavior of the fluid that is in contact with the surface of the solid body. So we can say that the fluid and the solid constantly interact with each other and affect each other. For example, the fluid constantly exerts a force on the surface of the solid, and the solid causes displacement in the surrounding fluid. Now, establishing these couplings between solid and fluid is the responsibility of the coupling system. For this purpose, in addition to using Fluent software for fluid modeling, transient structural must also be used in the ANSYS Workbench software. Also, in the Workbench environment, the tool coupling system should be used to complete the coupling work between fluid solution and solid solution. Of course, it needs to be mentioned that about the FSI method and its capabilities and applications, we will provide a comprehensive training in full detail in a separate and independent training course. The chapter 1 has ended, and in the following we will simulate a cylinder piston motion in order to introduce the in-cylinder model. To benefit from MR-CFD services including simulation, consultation, and training, visit our website via www.mr-cfd.com or contact us via info@mr-cfd.com.